Hi everyone. I've got a little talk today about some revolutions, big ones and small ones. On the science side, it's mostly science, this talk. We're going to look at the detection of the faintest of signals, very small revolutions there, but their massive impact for human knowledge. We're also going to look at the hugely powerful infrastructure that's needed just to make this possible, and the small part that OpenStack is playing in making that revolution happen. So I'm going to talk about the quiet revolution that's going on. It's underway with OpenStack in scientific computing. I don't know if anyone's noticed, but the schedule at an event like this tends to have more and more talks based on content from research computing, as well as enterprise and other pieces of cloud and so on. I'm going to talk about the way that conventional scientific computing infrastructure really doesn't satisfy the way that people can use OpenStack and the things that OpenStack can do that take it above and beyond the way that conventional science computing kit goes about and working. So I'm going to make the case that OpenStack and scientific computing have got a long and bright future together, and perhaps it's time that they all paid a bit more attention to one another. So, my name is Stig, and I've been very privileged to be involved in several luminary companies in scientific computing over the last 20 years. Today I work as part of a very small, very talented startup based in Bristol and across the UK. And what we do is we are developing OpenStack infrastructure specifically for meeting the needs of research computing projects around the UK and Europe. So, we're going to lay the scene with something that actually I've never had anything to do with, but as a sort of enthusiastic amateur scientist, I think it's pretty cool. So this is a machine, it's called LIGO, and what it does is it can hear gravity. It's a project that started operation, so it only really started working 2 years ago, September 2015, and behind that was 40 years of hard work and persistence, sheer bloody-mindedness, testament to ingenuity, determination, and perseverance by the people behind it. So LIGO is actually two machines. This is one of them. They are L-shaped vacuum tubes, 4 kilometers long, in opposite corners of the United States mainland. And what they've got down the middle is, in the vacuum tube, they shine a laser beam down the middle, and then at the right angles, they shine another laser beam, and they see the interference at the point where they meet. And what they can do then is they can detect very, very tiny changes in the length of the tube. And why that's useful is that when gravity waves pass by, theory predicts that they kind of make space wobble a bit like a jelly, and they can detect whether the tube is getting longer or shorter. And this machine is incredibly sensitive, but it's really only able to hear the very biggest gravity wave events that the universe emits. So what it's tuned to detect is the collision of two black holes. And it took just 10 days from it starting to hear its first collision. So it's a busy place, the universe, it turns out. But black hole physics, the numbers get quite extreme pretty quickly. So the detection that it made were two black holes, which they estimated were 36 suns and 29 suns in terms of their mass. And when they collide, they spin together, and then eventually they hit, and they give off a massive flash of energy. That energy is measured in terms of the amount of matter that would be the equivalent of that energy. And there's only really one other thing that we can think of which is in the same sort of frame of reference, and that's a hydrogen bomb. So the biggest hydrogen bomb that man has ever made is the Soviet Tsar bomb, which was 50 megatons. It gave off about 2 kilograms of matter in terms of the energy of that H-bomb. But this black hole collision emitted the weight of 3 suns in energy. In a tenth of a second, it gave off more energy. It was the brightest thing in the universe. It was brighter than everything else in the universe put together for a tenth of a second. But no one saw it because it was all in gravity. So now we have this machine, this LIGO machine, and it can see or it can hear gravity, and it can hear this world, this galaxy, this universe out there, which we've never been able to perceive before, which is a pretty cool thing. LIGO was able to detect it, but it was the distance change in the length of those vacuum tubes was the equivalent of 1,000th of a radius of an atomic nucleus. It was really on the boundary of what you can imagine as being detectable. It's a pretty cool machine, but it can only really see the tip of the gravitational iceberg. So that brings us a little step closer to what we've been working on, because there's a new project coming along which is going to use one of the wonders of deep space to catch another, and that is the Square Kilometre Array. So the SKA is proposing to use pulsars, these collapsed stars that are spinning fast and emitting radio pulses at a very, very good regularity. So they're going to use those instead of the vacuum tube. And out there, they're going to choose a pulsar which is blipping away. And then they choose another one. They build up a whole mesh of these things. And by measuring very slight variations in the phase of the pulsars, they can actually hopefully perceive the way that gravity waves are passing through the solar system. Gravity waves can be really, really big. They could be the order of the solar system in terms of the wavelength. They're talking nanohertz rather than gigahertz. So a machine of that scale makes it possible, theoretically, for us to see it. So that is taking this new way of perceiving the universe even further. It's not just about detecting gravity, though. This is possibly the biggest graphic you're going to see. It's the entirety of universe for the entirety of time. So it is the total perspective vortex. And one of the other goals of the SKA project is to be able to look back further with greater sensitivity back to the beginning of time, the Big Bang. So we can hopefully start to see the background radiation and the point where the first luminous objects started to be created. So we should be able to see that even more clearly, the cosmic dawn. The machine itself is actually two arrays of detectors. So there's the low-frequency telescope and the mid-frequency telescope. This is if you'll excuse the pun, this is an aerial view of the detectors, the antennae in the low-frequency array, they just look like TV aerials stuck in the ground. There are going to be, when it is deployed, 130,000 of these little antennae stuck in the desert in Western Australia, generating every year 130 petabytes of astronomical data. The mid-frequency telescopes are more your conventional idea of a radio telescope. This is 3 of a 36-dish prototype, the Australian SKA Pathfinder, which is also in Western Australia. So there's a lot of prototyping activity that's going on already in terms of the antennae and the dishes. But the piece that I want to talk about is the compute problem, the piece that backs all this up. So we take all this data, we take this data from these vast streams, these amazing feeds. How do we make sense of it, and how do we build this picture of what we're actually observing? So the compute problem is the only other thing I can think of that comes close to the numbers of black hole physics. And the science data processor, the machine at the heart of the SKA, is a machine that must consume every day 50 petabytes of correlated data from these antennae. It has to consume 50 petabytes every day and digest it. It has to hold this data for 6 hours, and it has to hold the digested data for 6 months. That's a huge processing challenge, and it's a huge data challenge. The estimate of the SKA consortium is that the science data processor at the heart is going to need to be about 250 petaflops of compute power when it goes into production in about 5 years or 6 years' time. So much of that compute power, I'm going to just skip over this bit, partly because I'm not such a great mathematician either, but much of the compute power is powering the interferometry mathematics that enables these multiple telescopes to work together as a single coherent device. So interferometry works by varying phase between the different detectors that are laid out across the ground, across this thing they call the baseline. And what happens is if we change the timing of all of these signals and we correlate them together but according to different phases, then in amongst this great mountain of noise, we can tease out the faintest of signals that they are all perceiving from the same region of sky. That's how it works. The signal-to-noise ratios are crazy, but it is able to find with huge accuracy, by combining huge amounts of noisy data, the tiniest of signals. There's also a huge data challenge here. So if you look down at the bottom, there's this thing called a sky image. These are the sort of the building blocks of the SKA's data set. A 30K by 30K by 64,000 color or 64,000 frequency image is 64 trillion data points. So in 8-bit graphics, that would be 60 terabytes per frame. And of course, it's a good deal more precise than that. So this is a huge thing that has to be sampled time and time again as quickly as the telescope can consume them, and then stored away and made use for primary and secondary science purposes. Obviously, there's also a good deal of other things that the SKA must achieve. It can't just be a fancy camera. It has to also do the analysis on the data that it is gathering so that it can look and see when things are happening. So when things are happening in the sky, when there is something like a supernova or some other sky event, it needs to say, hey, stop all this programmed observation. Look, something really interesting is happening over there. Turn everything around and look at that. So there are huge software challenges in terms of the application to process this thing. It's not just about digesting vast amounts of data scaled out. It also has to have this near real-time component in order to be able to respond effectively. So the compute requirements far exceed today's capabilities. And this is what the biggest computer in the world today looks like. It's actually taken from the ground. It's not actually that tall. This is the Sunway Taihu Lite in China. It's 93 petaflops. Biggest computer in the world today. Does look, I think, a bit like Deep Thought from The Hitchhiker's Guide, but even for that, it still falls far short of what the SKA needs. So we look at what's in the pipeline. So next year, end of next year, the US Department of Energy is buying 3 big machines. This is one of them. It's called Aurora, obviously. And that's $200 million worth of computer. That is going to be 50,000 compute nodes of the best that you can buy today. It's about 180 petaflops, so it's still not quite big enough. It's far too expensive. It uses far too much power. And it's also far too special in many ways. What the SKA needs is something which will deliver 250 petaflops 5 years later, and it needs to get it at off-the-shelf pricing. So how do we go about doing that? We're getting closer now, aren't we? So the best guess that we have today for how the science data processor, the SDP machine, will look is something which looks very much like a multi-network cloud environment. So we have multiple networks inside the machine. We have the 50 petabytes a day coming in from the top from the signal processors next to the telescopes. And then we also need to have these very tightly coupled networks for east-west traffic. We get scalability by creating a loosely coupled scalable grouping of tightly coupled compute islands. So a compute island is like a locality in the machine and in the data problem that it's serving. There are a huge number of unknowns about this architecture still. And the purpose of the projects that we are doing is to help to prototype and to inform those decisions so that the architecture can be developed further. And this is our corner of the SKA project. It's called the Performance Prototype Platform, or P-Cubed. It's a machine that's hosted at Cambridge University, and its whole purpose is really to enable people to explore and to just using what's available today, the best kit you can get today, what are the promising contenders in terms of CPUs, networks, storage, software, algorithms, and infrastructure. So we provide this diverse range of cutting-edge hardware. We have real diversity in this machine. There's all kinds of different nodes, different storage activities, different network activities. And we're using OpenStack for bare metal infrastructure management to tie the whole thing together, to manage this diversity, and to present it to the users so that they can explore stuff without it also being really hard for them to get anything done on a cutting-edge, diverse environment. So the system we've got, well, that's half of it. It's a model of 2 compute islands. And I think it's probably a bit of an unwise extrapolation to predict the performance of tomorrow's hardware based on the hardware of today. But it's certainly, from my perspective, good fun. And it's certainly going to help inform the questions of which are the viable directions to follow further. So I guess that there's a fundamental early question which most people in the cloud world will be asking at this point, which is why are we using bare metal for this? We want to provide a convenient service for people to develop their algorithms and see how they're performing. So why bare metal? Why not virtualize? It's nearly as good. Well, I guess that it's one of those questions that you best answer in the context or the medium of robot Shakespeare, and like so many other questions these days, I guess. But when we create software-defined infrastructure, what kind of infrastructure are we really talking about? So OpenStack can support VMs, containers, bare metal. We all know this. But principally, this machine is about outright performance. And a lot of it is about I/O performance and network performance. So we don't want to be squandering any of the microseconds that we might be spending in hypercalls and other things if we virtualize. An I/O-centric system, the nervous system of that machine, works best and is most accurately measured in a bare metal environment, and that is still true today. But we do plan for VMs, for some of the non-critical sort of housekeeping services, the supporting roles, the mother hen, the other stuff around the side. And many of the workloads that are being prototyped are being developed in containers. So this system actually embodies all 3, but the greatest of those is the bare metal. So the control plane has requirements, obviously, for performance, but it also needs flexibility because so many of the different software environments that we are deploying are really, really different. So we're exploring with Spark, we're exploring with conventional high-performance computing, so sort of straight-line MPI performance. We're exploring with things like the Dask, the Python task distribution package. The idea is that we present the convenience of self-service of OpenStack, but at the same time, we give them the real deal in terms of the bare metal performance that they need. The reality of OpenStack infrastructure management for this machine is not always so perfect. Research computing use cases, in terms of OpenStack clouds, they can be like the black swan events. So we don't always assume in a cloud that every single node in the machine is going to get redeployed at one go. We don't assume that there are just one tenant, say, or just 3 tenants on a cloud. And cloud software services don't really have an assumption that networking is not IP-based, for example, which a lot of the networks we use are. So there's a huge amount that conventional HPC infrastructure has grown up around exploiting in terms of commonality and similarity between the different machines that it is managing, that a cloud completely assumes the opposite and assumes that everything is different and kind of depends on that. So these assumptions don't always stack up in a research computing environment. And how does OpenStack cope with these kinds of black swan events? Well, sometimes it does and sometimes it doesn't. We've got 6 years to iron it out. So the application frameworks I mentioned that we're looking at are themselves highly diverse. So we have to create this machine which provides all of these tools as well as we can. We need infrastructure that does this without sacrificing performance, and that's where our company came into the project. Our vision is this kind of polymorphic, reconfigurable infrastructure, specifically, though, one which can be tailored to any workload that's running on the system. So we can kind of retune the machine in order to serve Spark, in terms of where maybe we're looking for diversity, Hadoop, in which case maybe we're going to unrate the disks, or MPI, in which case we're going to turn off all the power-saving states and just run it as fast as we can. The platform is bare metal, but we don't want to sacrifice any flexibility for it being bare metal. But Ironic is easily the coolest project in OpenStack in terms of the speed in which it is developing and the direction that it is going. So we work as upstream as we can to make use of the very best bits that Ironic is delivering. And we've been working on the last cycle or two on some of these features, so zero-touch registration and enrollment of our nodes. Being able to deploy scalably is something we're very interested in, obviously. We've delivered the multi-network support with Sam here, actually. Thank you, Sam. And next, we're looking at how do we adapt the firmware in service of the flavor. So that's where we are with Ironic. We also, because this is a performance prototype system, we really want to be able to offer to the users the kind of information that we can get as administrators and the kind of information that they can get as scientists from other machines. So we want to be able to package together all of the performance telemetry data that's coming through the system. And Manaska is it, basically, for that. In terms of if you want to be able to provide to your users data from telemetry and so on, and for their workloads and for their instances, and logging data and all these other things, package it up together, then that is why we use Manaska. And this was just a simple example. We fire up a number of compute nodes, and we can see some interesting things. So we can see here that the CPU frequency is actually scaling up and down while we're running a workload. It's not the best example, but it's the easiest one I had at hand. So how do we do this? So we had some good experiences previously working on deploying OpenStack, but we'd always come up against this problem of, well, how do you actually then upgrade the machine? So we could take a machine and we could add in a lot of HPC-like features, but the dependency layers that you would start to accrue would soon get to be pretty hellish. So then we started to work with Collar, and containerizing the OpenStack control plane is the solution to being able to upgrade a complex system like this one. So the way that we do it is using Collar and Ansible through and through. And we created, in a very, very similar manner to the way that OOO works with the Undercloud Director, we create a very small seed VM, and into that we put Bifrost, and we put an Nginx repo, web repo, and that's it. So it's a pretty simple, minimal seed starter to deploy the machine. Everything else that we do is done using Ansible, and then that deploys Collar, and then Ansible again configures Collar and builds the cloud on top of that. So I'll quickly take you through how it deploys, and I'll just whiz through this bit. So we have a machine. It's got CentOS on it. We deploy a VM, and then into the VM we put two containers, Bifrost and Nginx. We have our SSH keys, and then we can start to talk Ansible to this thing. We then start to build up the hardware inventory. So we've got a pile of switches and a pile of compute nodes. We use Ansible again to drive the BIOSes and to configure the switches. So the Ansible network modules come in, and we have some modules for where we can talk to BIOSes like the DRAX. We can configure BIOS and RAID to a baseline config and bring them up. So what we've got there is a pile of kit that's just come in off the loading dock, and a source code repo, which is infrastructure as code. So it's everything is under version control. It then we start to image the nodes. So then we have a nice multi-node control plane. We have broken out the roles onto different servers and put the whole lot behind load balancers in the conventional form. And then we start to deploy Collar containers on those servers. So that's actually then the bare control plane is brought up. And then we do further Ansible playbooks to apply site configuration. We define our flavors, our provider networks, the storage access, all these other things are built on top of this. So it's layers upon layers of different Ansible configuration running from start to finish. in an automated process. So then we get a bare metal machine, and we can have a number of tenants on it. And because we like to use Ironic in its best way, we have multi-network support. So they have Ironic managing VLANs, again by talking to the switches and manipulating the physical port memberships. But then this is kind of not enough, really, because what we've got there is we've just given our users servers. We've given them infrastructure. It's not helpful enough. So we can start to... where did that go? We can start to then build up platforms, clusters, scientific applications as a service. And because we are using this cloud model, for each of these different users, we can deploy a totally different runtime environment. So maybe there are bioinformatics, maybe there are physicists, maybe there are chemists. They all have different requirements. And the wonder of cloud is that instead of managing one giant resource and it's one size fits all, we can say you can hire this resource or you can allocate this resource yourself and run it the way you choose. And we will support, with a very nice delineation, the infrastructure, the platform, and you guys look after the application. But we don't have to stop there. Why would we? Because we've got this far. So our workloads are also using some of the sort of more modern data analytics stacks, as well as conventional sort of traditional MPI and Slurm. So now we've got this interesting situation where we have other requirements in terms of we've got throughput-oriented workloads, we've got I/O-intensive workloads, as well as these compute and network-intensive workloads. So we need to have a machine which is optimized in each of those cases for the workload that it's running at that particular time. And why stop there? I mean, we could run containers as well, we do, or we could run a mixture of everything and anything on the same machine. So this is really the joy of OpenStack for our use case. It provides a policy and a mechanism, and the users can choose how it gets used ultimately. This is not the one-off. There are many machines out there in research computing which can and are used in this way. And here's another example. So this is a bioinformatics machine for DNA analysis, genome sequencing. And I don't know if you can see the details there, but there are components of MPI, components of Hadoop, MongoDB. There is something of everything in here. And to make this machine run as well as possible, you need to have this kind of dynamic polymorphism, this ability to reconfigure and optimize according to how the machine is needing it. Currently, you can only get that from hand-built systems. So OpenStack is bringing in a very good, very cool, very, very exciting new capability in the next release or the one after. So there's still a few things that don't quite work. If you look at the sort of the modal size for OpenStack is still 10 to 99 nodes. And the complexity of the control plane is still a problem. We do find that the using containers and using Collar enables us to upgrade, and we have been upgrading some machines to OpenStack Pike in the last week, and that's all gone a hell of a lot better than it would have done if we weren't containerizing things, so we're pretty pleased with that. Generally, in the scientific case, the utilization is still a problem. So how do we make use of idle cycles on a cloud system? And that is a problem that, for OpenStack, I think, is still there. And it's something that we are working to advocate, I guess is the word. And the way that we do that is that we've got this special interest group called the Scientific Working Group, which is about bringing people together who all have this problem or all have this interest and are looking to make this happen. So this has been going for about 2 years, and we have been, there's probably about 50 to 100 people who turn up at the summits and go out for beer and talk science and working and OpenStack infrastructure together. The way that we work is that we share information. We advocate the use cases of science within OpenStack, and we advocate OpenStack within the scientific community as well. One of the things that we did for this was to write this book, which we gave away at the Supercomputing conference, and we've just started on a second edition of that book. So it's a pretty exciting thing. If you're in research computing, it's well worth taking a look. scientific computing sees the attraction of OpenStack, and we get the impression that feeling is returned as well. So last year we had the pleasure of entertaining Jonathan Bryce and Lauren Sell from the OpenStack Foundation at Cambridge University before the Austin Summit to celebrate the launch of OpenStack Newton. And Cambridge being Cambridge, they got out a copy of Isaac Newton's seminal work, Principia Mathematica, for Jonathan Bryce to hold. It's not the same Newton, but, you know, who cares? Which, in a very nice way, brings us full circle onto gravity again. So I do like a good bit of closure. So if you're interested in science and you're interested in science on OpenStack, do come along to the scientific working group. Actually, we have like a birds of a feather session later on, 4 o'clock today. So hopefully I'll see you there. And thank you very much. Do we have any questions?
Do you have any integration of InfiniBand in your control plane? Stack, or is it really just a flat network that's...
Yes, we do. So the subnet managers run on the control plane in a container alongside the other services. But the exciting way that InfiniBand can be used in that context is in iSCSI over RDMA. And we've used iSCSI over RDMA on Rocky, so over RDMA-enabled Ethernet, not on the clouds that have InfiniBand at the moment, but it remains there as a possibility. So there's some interesting pieces. If you're using bare metal, then the whole model of how you connect Cinder volumes to bare metal instances is something that's still a little bit formative. So it's one of those ones to watch the space.